Section 9.4, Applications, Distance, Rate, Time, Number Problems, Amounts, and Costs. The objectives: use systems of linear equations to solve distance, rate, time application problems. Use systems of linear equations to solve number problems. Use systems of linear equations to solve amounts and cost problems. Example 1 is an application of distance, rate, and time. A small plane flew 300 miles in 2 hours, flying with the wind. Then on the return trip, flying against the wind, it traveled only 200 miles in 2 hours. What were the wind speed and the speed of the plane? Note, the speed of the plane means how fast the plane would be flying with no wind. The solution, we're going to let S equal the speed of the plane and W equal wind speed. It is a good idea, if you can, to choose variables that are similar to the words in an application problem, so you don't have to necessarily think about what is X and what is Y. You can use any variables you want. When flying with the wind, the plane's actual rate will increase to S plus W. When flying against the wind, the plane's actual rate will decrease to S minus W. Note, if the wind had been strong enough, the plane could actually have been flying backward away from its destination. The distance, rate, and time problems are best solved using a table. So you'll notice here we have a table. We have rate times time equals distance. So that's the formula we're going to use. And then we've determined what the rates are for each situation. One situation is with the wind. The other situation is against the wind. So the rate with the wind is S plus W. The rate against the wind is S minus W. In both times or situations, they flew for 2 hours. The distance then becomes rate times time. So for with the wind, it's 2 times S plus W. For against the wind, it's 2 times S minus W. We'll use this table to help us write equations. So the system of linear equations is going to be the following. 2 times S plus W is equal to 300. That's with the wind. 2 times S minus W is equal to 200. If we go back, we did that because we knew that when it was flying with the wind, it went 300 miles, so that was our distance. When it was flying against the wind, it only went 200 miles. That's where this 300 comes in and this 200 comes in. Apply the distributive property to the left-hand side of each equation to find an equivalent system of equations, then use the addition method to solve the system. So when we distribute, you're going to have 2S plus 2W equals 300 for my with the wind equation. And we're going to have 2S minus 2W equals 200 with against the wind. This is nice because I don't even have to worry about multiplying. I'm simply going to add these together because these two already have the same coefficient but opposite signs. When I add these equations together, it ends up giving me 4S equals to 500. When I divide both sides by 4, S, which is the speed of the plane, is 125. Back substitution with S equals 125 into my original equation, 2 times S plus W equals 300. It's going to give me 2 times 125 plus W equals 300. I will distribute here. Or actually, we divide both sides by 2, and that gives us 125 plus W equals 150. Subtract 125 from both sides. This W is equal to 25, which is the wind speed. The speed of the plane was 125 miles per hour, and the wind speed was 25 miles per hour. If you were to check those, you would see that that is accurate. Example 2, another distance, rate, time problem. 2 buses leave a bus station traveling in opposite directions, not trains, but buses. One leaves at noon, and the second leaves at 1 p.m. The first one travels at an average speed of 55 miles per hour, and the second one at an average speed of 59 miles per hour. At what time will the buses be 226 miles apart? So you have the buses here. And you'll notice in these equations, this bus is traveling 55x miles, this bus is traveling 59y miles. So they're using X and Y. And then you'll notice this total distance, which we actually know, that total distance is the 226 miles. Once again, we're going to set up a table. X is going to be the time of travel for the first bus. Y is going to be the time of travel for the second bus. We know bus 1 was going 55 miles per hour, so that's the rate. Bus 2, 59 miles per hour, so that was the rate. Again, bus 1's time is X, bus 2's time is Y. The distance is just rate times time, so that's 55x and 59y. And I do know my total distance, so that's going to be one of my equations. That's the equation I'm talking about here. 55x plus 59y is equal to 226. That's the sum of the distances being 226. The other equation that we're going to write is we know that the first bus travels 1 hour longer than the second. So if X is how long the first bus travels, the second bus travels Y plus 1. Y is the second bus, which is what? Let me start again. Sorry. The first bus, X, is traveling 1 hour longer than the second bus. So it's the second bus, which is Y plus 1. Now we'll use the substitution method to solve the system. And when you're in the application section problems, you get to choose which method you want to use. Graphing is probably not going to be the most useful because it's not always accurate. But you can use substitution or you can use addition. The reason we're choosing substitution here is because this equation is already solved for X. So I'm going to replace the X here with Y plus 1. So 55 times Y plus 1 plus 59Y equals 226. When I go ahead and distribute, I get 55Y plus 55 plus 59Y equals 226. Collect like terms gives me 114Y on the left. Subtract the 55 from both sides gives me 171. Now I will divide both sides by 114. So Y is 1.5. Back substituting in the first equation, which was X equals Y plus 1, is going to give me X equals 1.5 plus 1, which is 2.5. So the first bus travels 2.5 hours, and the second bus travels 1.5 hours. So the buses will be 226 miles apart at 2:30 p.m. Again, we'll know that one bus leaves at noon, the other bus leaves at 1. So if the first bus is traveling 2.5 hours, that's the bus that left at noon, so that would be 2:30. That's how they're coming up with the 2:30 p.m. You should consider making tables similar to the ones that we illustrated in these examples when you're working with application. Those tables can help you organize your information and keep things organized. Our third example, the sum of two numbers is 80 and their difference is 10. What are the two numbers? We start by defining our variables. So we're going to let X equal one number and Y equal the other number. And then the system of linear equations are going to be the following. X plus Y equals 80. We get that because we know the sum is 80. And our other equation is X minus Y equals 10. And we know that because the difference is 10. Now once again, we're going to use the addition method, and we don't have to do much work here because the coefficients on my Y are same sign, opposite, same number, opposite signs. So they're going to eliminate. So when I add these together, I end up with 2x equals 90. And if I divide both sides by 2, x is equal to 45. When I back substitute 45 for x in the first equation, I have 45 plus y equals 80. Subtract 45 from both sides, y equals 35. The two numbers are 45 and 35. And we can check that by plugging those in, and we see that 45 plus 35 really is 80, and 45 minus 35 really is 10. Example 4 is counting coins. Mike has $1.05 worth of change in nickels and quarters. If he has twice as many nickels as quarters, how many of each type of coin does he have? We're going to use a table again here. We use two equations, one relating the number of coins and the other relating the value of coins, or your dollar amount. You know that the value of each nickel is 5 cents and the value of each quarter is 25 cents. And again, we're going to use variables that represent our words. So we're going to be using N for nickels and Q for quarters. So our coins are nickels and quarters. The number of coins we have are N for nickels, Q for quarters. Our value in cents is 0.05 for a nickel, 0.25 for a quarter. So if I want to know how much money I have, I can just take the number of coins I have times their value. So that gives me 0.05 nickel and 0.25 quarters. The system of linear equations are going to be the following. The easiest one to see right off the bat usually is actually the second one. So if I take 0.05 N plus 0.25 Q, that gives me my total dollar amount of $1.05. This equation is based off of the statement, there are 2 times as many nickels as quarters. So our nickels is equal to 2 times the number of quarters. So it seems backwards, but you just have to understand that you have more nickels than you do quarters. So if you were to plug numbers in and try it, you see that N is equal to 2 times the number of quarters. So you've got to be careful that in the first equation, Q is multiplied by 2 because the number of nickels is twice the number of quarters. Therefore, the number of nickels is bigger. So that's important to remember. That one trips people up sometimes. I'm thinking substitution is probably going to be our best bet here. So the first equation is already solved for N. So we're going to substitute Q2Q for N in the second equation, which is 0.05 N plus 0.25 Q equals 1.05. 0.05 times 2Q plus 0.25 Q equals 1.05. So 0.1 Q plus 0.25 Q equals 1.05. Now we're going to multiply everything times 100 so we can get rid of decimals, which is always a good thing. So 10Q plus 25Q equals 105. Essentially, you're just moving your decimal place over 2 to the right. 10Q plus 25Q is 35Q equals 105. Divide both sides by 35. Q is 3. So you have 3 quarters. And since you have your nickels are twice as many as your quarters, you have N equals 2Q, which is equal to 2 times 3, which is equal to 6. So 3 quarters, 6 nickels. Example 5 is calculating age. Kathy is 6 years older than her sister Sue. In 3 years, she will be twice as old as Sue. How old is each girl now? This problem we have to represent what Kathy and Sue's age are now and what Kathy and Sue's age will be in 3 years. So we'll start by looking at Kathy is K. That's her age now. Sue's age is going to be S. That's Kathy's age now is K. Sue's age now is S. So that's their first set of equations. All right, and then the system of linear equations is as follows. K minus S equals 6 because we know the difference in their ages is 6. And we know that in 3 years, each age is increased by 3, and Kathy is twice as old as Sue. So K plus 3 is Kathy's age in 3 years, and that's twice as the age of Sue in 3 years, which is S plus 3. We're going to rewrite the second equation so that it's in standard form, and we can solve by addition. So I have K plus 3 equals 2S plus 3. 2 times S plus 3. So when I distribute on the right, I'm going to have K plus 3 equals 2S plus 6. And then I'm going to subtract the 2S from both sides and subtract the 3 from both sides, which is going to leave me K minus 2S equals 3. So I rewrite those equations together here. K minus S equals 6. K minus 2S equals 3. And I'm going to multiply the second equation times -1. So I just transfer K minus S equals 6 here. And when I distribute the negative 1, I'm going to have negative k plus 2s equals a negative 3. I'm going to add those two together. You'll notice the k's are going to be eliminated. When I add those together, s equals 3. So Sue's current age is 3 years. When I back substitute s equals 3 into one of my original equations, we'll go with k minus s equals 6. So in this case, k minus 3 equals 6. Add 3 to both sides. K is equal to 9, and that's Kathy's current age. So Kathy's 9 years old, and Sue is 3 years old. Example 6, another finding amounts and costs. 3 hot dogs and 2 orders of French fries cost $10.30. 4 hot dogs and 4 orders of fries cost $15.60. What is the cost of a hot dog? What is the cost of an order of fries? We're going to let x equal the cost of 1 hot dog. We're going to let y equal the cost of 1 order of fries. The system of linear equations is going to be as follows. 3x plus 2y equals $10.30. So 3 hot dogs, 3 x's, 2 fries, which is 2y, is $10.30. Our second equation is 4x plus 4y equals 15.60. So 4 hot dogs and 4 French fries is $15.60. I'm going to take the top equation times a negative 2, which is going to give me negative 6x minus 4y equals negative 20.60. Transferring over the other equation, 4x plus 4y equals 15.60. When I add these two together, the y's are going to be eliminated. It leaves me with negative 2x equals negative 5. Divide both sides by negative 2. X is equal to $2.50. That's the cost of 1 hot dog. I can back substitute x equals 250 into 3x plus 2y equals 1030. And 3 times 250 plus 2y equals $10.30. 3 times 250 gives me 750 plus 2y equals $10.30. I'm going to subtract 750 from both sides. It's going to leave me with 2y equals 2.80. Divide by 2. Y is equal to $1.40. The cost of 1 hot dog is $2.50, and 1 order of French fries is $1.40.